Sciences View Pre-Calculus. We're doing topic 8, which is solving trig equations, and in this video we'll do examples 4, 5, and 6, all of which involve solving a trig equation where neither side is currently 0. So we are finding solutions on the window from 0 to 2 pi, which is essentially 1 full unit circle in radians. Okay, so in example 4, the first thing we have to do is make one side equal to 0. I want to caution that some of us have this natural gut instinct that is wrong here. Some of us want to divide by sine x because we see the sine x on both sides and we're like, cool, if there was a 5 in front of things and a 5 on the other side, just divide by 5. You can't do that with sine x, and here's why. Sine x is a variable expression that sometimes equals 0, and since you're not allowed to divide by 0, dividing by that variable expression will essentially lose answers that are important to getting the right answer. You're going to accidentally delete those answers where sine x is 0. So there are ways around that, but the safer way to play this is that you don't divide, you move everybody to one side and you factor. So I'd rather keep this complicated term positive, so I'm going to subtract the sine x over. So I'm going to get sine of x times tangent squared of x minus sine of x equals 0, right? So the 0 step of factoring makes sure one side equals 0. I'm then going to go ahead and use that GCF, right? We've practiced using a GCF. I take out a sine, and I'm going to be left with a tangent squared x minus 1 equals 0. Now, at this moment, you could actually just solve. Tangent squared x minus 1 is a difference of squares and is something that you could continue to factor. But if you didn't see that, you could also solve the way it is, and I'll walk you through both options. So if you wanted, you could actually factor this into a difference of squares, because tangent squared is a perfect squared, so is 1 squared, right? So you could make this a sine x times tangent x plus 1 times tangent x minus 1, and that's fine. I'm going to show you how you'll get the same answer either way. So if you did this, right, you would get that either sine x is 0, or tangent x plus 1 is 0, so that's the same as saying tangent x is negative 1, or tangent x minus 1 is 0, so that's the same thing as saying tangent is a negative 1. These two are going to be the same answer you get if you just solve this. Because if you just solve this, you would say, okay, cool, sine x could be 0, or tangent squared x minus 1 could be 0, tangent squared x could be 1. When you write a square root in a problem, you have to write plus or minus. So you would get that tangent x is a plus or minus 1. And notice that these two answers are the same as these two answers. So I don't care which way you come to it, but you'll get these three values. That sine is 0, that tangent is plus or minus 1. I don't care how you come to it. So now we actually have to solve. But again, it doesn't matter which of these two options you pick, you're going to get to the same spot. So let's go ahead and we'll just do it this way. It doesn't really matter. So sine is 0 is the same as saying when the y on the unit circle is 0, which we've seen in a couple problems is at 0 and pi and 2 pi. So my answer here would be x is 0, pi, and 2 pi. Now, if tangent is 1 or negative 1, right? So think about what tangent is. Tangent is the y on the unit circle on top of the x in the unit circle, and that's a negative 1 here. What that's saying is that the y on the unit circle is the same number as the x on the unit circle, but opposite signs. The only place that the x and y coordinates are the same numerical value are at the pi over 4s, those 45-degree angles. And if I want the signs to be opposite, that has to be in quadrant 2, where I have a negative sign and a positive sign, and in quadrant 4, where I have a positive sign and a negative sign. So the answer to these two, where my tangent would be a negative 1, is they're going to be the 3 pi over 4 and the 7 pi over 4, right? And then if I want to answer where tangent is a 1, well, it's the same math, except instead of having that negative 1, it's just got a 1, right? So really, it's asking where are the x and y coordinates exactly the same? Well, it's the same pi over 4s, but in the opposite two quadrants, because I need where the signs are the same, either positive over positive or negative over negative. So basically, the short version is I'm going to end up with all the pi over 4s, right? So you could have maybe spotted that if you'd done it this way, but these are my answers, right? There are 7 of them, all right? So interestingly enough, if you had that gut instinct that I mentioned at the start of the video, and you had divided by sign, what would have happened is this would have been gone and you would have only gotten these 4 answers. So when we divide by a variable expression, the caveat is that you actually can do that as long as you understand that by doing that, you're losing answers where that variable expression equals 0, so you have to find those answers and include them. I don't usually suggest that because I think a lot of us would forget to do that, so it is much safer to say, hey, I see a bunch of trig functions, I move everybody to one side, and I factor. But that's sort of the gist. Let's walk through example 5. So same setup, just a different equation. So in example 5, we have negative sine squared x minus 4 cosine x equals negative 5. So example 5, negative 4 sine squared x minus 4 cosine x equals negative 5. Okay, so here's the thing. In topic 7, we learned a trig identity that was useful. So in topic 7, I think it was in 7, we learned that sine squared theta plus cosine squared theta equals 1. This is one of the most useful trig identities that you're going to find. It actually makes total logical sense if you think about Pythagorean theorem, right? The x on the unit circle, the y on the unit circle, and the 1 unit. If you did Pythagorean theorem, your y squared would be sine squared, right? We already know y on the unit circle is sine. Your x squared would be cosine squared, and your hypotenuse squared would be 1 squared. So that's where this comes from. So here's the issue here. I look at this, and I move everybody to one side first, right? Or I don't. It's up to you if you start there. But I'm going to suggest that it's easier if you start with one side equaling 0. So I move the 5 over because it's the easiest option, okay? Here's the problem. When I look at this, I really want to be like, oh, hey, this is a secret quadratic trinomial. Here's my u. The problem is that this is not u squared, right? If my u was a cosine, sine squared isn't my u squared. So I need cosine stuff, right? The reason I need cosine stuff is that I'm stuck with this linear term. There's nothing I can do to change the linear cosine, but there is a really useful trig identity that would let me replace sine squared stuff with cosine squared stuff, right? So I need cosine squared stuff. So if I take this trig identity and I solve for sine squared, right, I could subtract the cosine over, I'd get that sine squared theta is the same as a 1 minus cosine squared theta. This is what I'm going to replace that sine squared with so that I'm able to factor this. So what's going to happen, and I'll kind of inch it so you can see both sides, I'm going to take this sine squared that's a problem and say, okay, cool, that's a negative 4 times 1 minus cosine squared of x, right? I used theta here to show you that it was just a general rule and it wasn't the same equation. But here, since it's sine squared x, it would be cosine squared x, not theta. Minus 4 cosine x plus 5 equals 0. If I clean this up, I get negative 4 plus 4 cosine squared x minus 4 cosine x plus 5 equals 0. So 4 cosine squared x minus 4 cosine x plus 1 equals 0, right? So now I can go ahead and do that u substitution because, see, if I made my cosine u, this cosine squared would be u squared, right? So this is a 4u squared minus 4u plus 1. When I factor this, this is either a 4u and a u, or it's a 2u and a 2u. The backseat has to be a 1 and a 1. I know the signs have to be the same, and that those signs both have to be negative. So it becomes pretty apparent pretty quickly that I need to do 2u minus 1 and 2u minus 1. The 4s won't work. They would, if I tried using the 4u and the 1u, I would end up with 5 in the middle, not a 4. So let me give myself a little bit of space. So if we come up here, I have this 2u minus 1 times a 2u minus 1, so that's going to be a 2 cosine of x minus 1 times a 2 cosine of x minus 1, and that equals 0. Since they're the same factor, I could set them both equal to 0 separately, but there's not really a whole lot of point. So I'm just going to get that the answer is whenever cosine of x is a 1/2. Well, the cosine is the x on the unit circle, right? And the x's are a half at the pi over 3's. And if I want the x's to be positive, I need to be to the right of the y-axis. So my answer is going to end up being that x is pi over 3 and 5 pi over 3. Just the 2 answers on this one. Okay, so a lot of work, but just the 2 answers. All right, last example is again going to involve using a trig identity. But this time when we see that sign of 2x, we hopefully think, hey, I know a trig identity that deals with that. So when we do E6, I have sine of 2x equals 2 cosine of x. And I say, oh, wait a second, I know that I can't deal with this 2x being on the inside, but I do have a trig identity that makes this 2 sine of x cosine of x, right? And then I'm going to subtract the other cosine, the 2 cosine of x over, right? When I look for a GCF, I see that I have both the 2 and the cosine x, so I can take out a 2 cosine of x, and what will be left is a sine of x minus 1. Right? So either 2 cosine x equals 0, which means cosine x is 0. So that's where the x on the unit circle is 0, and that's going to be here and here. Right? So those two answers would be pi over 2 and 3 pi over 2. Or sine of x minus 1 is 0. So sine of x is 1. That's where the y on the unit circle is 1. Well, that actually turns out to be an answer I already have. That's another pi over 2. That happens at pi over 2. So technically, I have